Thank you.
So, Alan, thank you very much for the invitation and for suggesting this topic. I have quite a few slides here, so I'm going to have to speak fairly quickly. And of course, as Alan suggested, he's recording it so people can watch it later. In addition, if people are interested in seeing the actual PDF file with the slides, I'm happy to email it to them. You can see my email address on the middle of the first slide. So I'm happy to email the PDF slide presentation to anyone who's interested. So I've got 8 parts to this presentation. As you can see, I've listed them on the left-hand side of the screen. The first question, of course, is why do we have skirts on hovercraft? I'll call that purpose here. And I think most people would say that the main purpose of a skirt on a hovercraft is to increase the clearance so one can travel over higher waves or rougher ground. But there are actually at least two additional reasons why one might put a skirt on a hovercraft. The first being is that you reduce the spray considerably, which of course is a big nuisance with air cushion vehicles. But a second interesting point, which I suspect a lot of non-technical people may not be interested, understand, is that if you do have a very large daylight clearance, as in this slide here, you have a very high momentum drag. So the drag on an air cushion vehicle is not only the obvious aerodynamic drag, but one also has wave resistance drag when traveling over water. One generates a system of waves, which increases the drag. And you can actually see very carefully, if you look at this diagram, you can see the vessel's got a slight bow up trim, and that's because it's trimming approximately parallel to the water surface. When traveling over water, the water is depressed, and that's experienced as the hovercraft has a slight upward trim on it. So the hovercraft has got to generate an additional force to overcome the wave resistance, but there's also this additional momentum drag, which I can send the formula for if anyone is interested in. So the skirt actually provides 3 advantages: increased obstacle clearance, reduced spray, and considerably reduced drag from the by almost eliminating the momentum drag associated with generating the air cushion vehicle. Here, of course, is a picture of the SRN1, which everyone is familiar with. This is almost the original version of the SRN1. It does have this bow structure on, which wasn't on the very first version of the SRN1. Here we see the SRN1 with what was then called a 6-inch skirt. Now, a lot of the my understanding of air cushion vehicles I've obtained by reading rather than speaking to people, because being in Australia, I don't really have many friends here who understand what a hovercraft is. So I have interpreted this diagram. If you look very carefully, the skirt seems to have an upward cut at the back. It seems to suggest to me that they recognized very early in the game that the stern skirt is problematic because of the scooping effect. Here we see the SRN1 with 4-meter skirt. I've converted that to metric units here, 1.22 meters. Again, one looks very carefully at this version of the SRN1, looking at the skirt, and one sees these, what looks to be joins. And I believe that is internal bracing to generate a double skirt, because even in the early days, the Saunders Roe company was interested in preserving the basic concept, which was an annular jet. And that idea is just about disappeared with modern skirts. Here's a picture of an early version of a skirt on the, not the earliest, on the SRN5 hovercraft, where we have a bag arrangement around the perimeter of the hovercraft. But the annular jet idea seems to be diminished because we can see the fingers, but these fingers are quite short. In later air cushion vehicles, the fingers, of course, have grown to about 1/2 of the total depth of the skirt. A rule of thumb that seemed to be used in the early days was that the height of the skirt that could be maintained was something like a quarter of the beam of the hovercraft. Anything much more than that would mean that you'd have problems with lateral stability. This is a very famous picture which was published in the Journal of the Royal Institution of Naval Architects, showing the development of skirts in the early days, going all the way back to 1959. So we're talking of over 50 years ago. The very first figure is one that's always confounded me, and if there's anyone here who can clarify it for me, I'd be pleased. It looks like on the very first skirt of the SRN1, they put an extension on the inside of the outer peripheral jet, which I find curious. I would have thought you'd put the skirt on the outside of the air jet. I've mentioned that to a few people when I've met them, and no one's been able to clarify it for me. I would say it would be more efficient to have the single skirt on the outside of the peripheral jet. Here we've gone to a double extension. We've got a skirt extension on both annular jets on the SRN1. And this picture here shows the, I presume everyone can see the pointer here on the screen. Here we see the extension on the annular jet of the SRN1. This really complicated construction to increase the height of the skirt. And you can see the intention of the design is to make sure you've still got a proper annular jet, and it's also facing inwards at an angle of about 45 degrees. The whole concept, of course, of the annular jet is just about disappeared when you go down to the bottom right-hand screen, where the skirt consists of a bag and fingers. Of course, the air is still going to leak out, as I'm showing with the pointer here. So you are going to get a stream of air like this, but not nearly like the original idea of an annular jet. Going back to the SRN1, you can see this complicated bracing. These are diaphragms inside the annular jet. That would have greatly increased the stiffness of the skirt, and that would be a fundamental problem with anything like this. The big advantage of the fingers, if we go to the bottom right-hand picture, the big advantage of the fingers is that they're very, very flexible. Second advantage of the fingers is you've got no joints, because wherever you've got joints in the skirt, you've got problems with wear and breakages. So the advantage of the fingers is the considerable simplicity compared to the early skirts. These pictures, of course, show a cross-section. The next picture shows plan view of the different kinds of arrangements. And in all cases, you can see there are curious design features associated with the stern of the air cushion vehicle. If you go to the SRN1, we can see a longitudinal keel, as it's sometimes called, in order to divide the cushion and to provide lateral stability. In this case, we've divided the cushion into 4 parts to give both longitudinal and lateral stability. Going to the SRN2, we can see the longitudinal keel plus 2 additional bags on each side, which can move outwards in the case of encountering an obstacle, hopefully not inducing too much drag on the vessel. By the time we get to the SRN5, we've actually progressed to probably what is the modern form of the planned form of an air cushion vehicle, namely straight sides for simplicity, a simple rounded bow, more or less a semicircle, and then the stern is usually straight to allow the design of the skirt at the stern. The stern skirt, of course, is the problematic part of the vessel in all cases, because the skirt at the stern always suffers the worst drag. Here we've got a picture of the one of the early skirts on the SRN1. It's possible to see the 2 sides of the extension to the annular jet. This must be the picture of the inside annular jet, not the outside one. One can see the rivets here, showing the attach, well, it shows you how it must be braced with internal diaphragms to maintain this complicated shape, which must have suffered a lot of wear and tear. This is the skirt on the SRN1 hovercraft when it was increased to a total height of about 4 feet, 1.22 meters. Looking very carefully at this, we can see the main part of the skirt here, and then the lower part, which is angled inwards at about 45 degrees because of this intention to maintain an annular jet pointing inwards and therefore providing it as much as possible some daylight clearance below the skirt. One can see these diaphragms as well, separating the two halves, the two sides of the skirt. Other people are interested in skirt designs. This is a picture of an early French craft, the Sedam N300. I presume it was because of copyright or patent reasons that they developed a different skirt system from those used in the early English hovercraft. The early Sedam vessels had a total of 8 inner skirts, which they called jupe, J-U-P-E-S, which I believe is the French word for a skirt. There are 8 of them, as I just said, 4 on each side. So you can see the rear starboard jupe here. They're slightly tapered, so they're cones, cone shape, which means that it properly inflates. Early experiments were performed on changing the angle, experimenting with different angles of the cone. And I have understood that I've read somewhere that in some cases, the angle was too shallow and the skirt didn't inflate properly. Now, in addition to the basic jupe, 8 of which are installed on this vessel, there's a skirt that goes around the entire vessel. I would have thought a skirt like this would suffer more drag, particularly the jupes. I thought they would have produced more drag than the skirt employed on the English air cushion vehicles. The next picture shows an underside view of the same craft, and it does look very complicated to me. In addition to the 8 jupe, which provide, of course, considerable stability, both longitudinally and laterally, in addition to the skirt that encompasses the whole air cushion, you've also got dividing skirt here. I would have thought such an arrangement would produce a lot of drag. Here is the N500. They tended to call their air cushion vehicles Navi planes. This differs from what I've showed you in the previous slides in a couple of ways. First of all, there are more than 8 jupe. You can see about a dozen on each side. And in addition, there's no peripheral skirt around the whole system. And one notices also the wrinkles in these skirts. The N500 had a number of problems. I understand operational problems. But ignoring them and just looking at the skirt, one can see that the jupe have changed form from the previous slide, and they seem to have put a bulge into them. This would have the interesting effect of slightly increasing the perimeter. If you think that perhaps they might increase the perimeter, the beam. If you consider that they might increase the beam by perhaps 5%, and perhaps they increase the effective cushion length of the whole vessel by 5%, that would be a 10% increase in cushion area, which would be quite a useful addition to the total lift obtained from the cushion. So that would be actually, that would provide quite a useful additional cargo carrying capacity. We're now moving on to something which represents pretty much the modern design of skirt, where one has a bag. This is the upper part, and the lower part consisting of the fingers. This arrangement is a little bit different still from the early bag and finger skirts, because it's not a complete bag at the top. It's only the top part of the bag. And for the lower part, you can see internal fingers here. So that means that you've pressurized the whole area here. So you've got a high pressure on the inside of the bag, and then the fingers, of course, are under pressure from the normal cushion pressure. The good feature of a skirt like this is that there are no joins at all in the skirt near the bottom where they're going to suffer wear. So there's going to be considerably less maintenance on a skirt like this compared to the earlier peripheral jet type skirts. The lowest joint is where I'm moving the mouse just now. An additional feature on this particular vessel, the Vosper Thornycroft VT1, is that you've got these control systems here where you can shift the skirt laterally in order to move the center of pressure of the cushion, and therefore be able to control the attitude of the craft. I don't believe that's used very much on modern air cushion vehicles. This is a diagram showing what the SRN4 skirts look like. We've got the upper bag, which consists of a loop, the lower fingers, and of course feed holes to feed the cushion air. And here you see the joints here, which are well away from the bottom where the skirt would experience the greatest drag. And this is one of only 2 pictures in my collection showing the skirt control system on the SRN5. So there was a system of chains. I believe there were 4 altogether, 1 on each of the 4 corners of the craft, whereby the skirt could be lifted up and therefore control the attitude of the cushion. And here you can see the port front skirt being lifted to some degree by this chain system. Later versions of the SRN5 involved puff ports on the side, and they got rid of that skirt control system. This shows you the skirt control system on the VT1. I showed you a picture of that a little bit earlier. You can see the upper loop, which only goes down to this point here. And then you've got the outer or the regular finger, and you've got the inner finger, which seals the upper loop. So this whole area here would be pressurized at something like 20 or 30% higher than the cushion pressure. And here you see the control system for shifting the skirt. I've shown this picture here because I find it interesting that the fingers run the full depth. It's not a bound finger skirt at the front. It's not a bag and finger skirt. It's a full depth finger skirt at the back. I see that Nia is logged on today. He might be able to clarify this more in the question time. This is a surface effect ship, so it's got side hulls. You can see one side hull here. So one only has a seal at the bow and at the stern. A big advantage of a surface effect ship compared to a fully skirted air cushion vehicle is that the skirt system is much less complicated. An early version of the skirt is the pericel skirt. So the pericel design consists of cells going around the perimeter. This was fitted to the Jeff A, going back, must be 40 years ago now, at least 40 years ago, when the Americans had a competition to design their air cushion landing craft. At that stage, they called it the AALC. Now, what does that stand for? Attack Air Cushion. Forgotten now. Attack Air Cushion Landing Craft, I think it stood for. There's a complicated story why they called it Jeff, which I won't say. And they had 2 versions of this, the A and the B. The A was the design developed by the Aerojet General Company, and then there was the B by the Bell Aero Systems. So you can see how the cells go all around the perimeter. it is claimed, I would have thought the effect would be small. It is claimed that the advantage of the paracel system is that once, for example, once the side of the hovercraft, say, drops closer to the water surface, you'd like to develop a restoring moment. The theory is that the pressure in those paracels increases and therefore corrects the attitude of the hovercraft. So there's no internal subdivision, which is an advantage. If you can get away from internal subdivision of the cushion, that makes the repair and the maintenance of the skirt system a lot simpler. It's occurred to me that another reason that the Aerojet people went to the paracel design is that perhaps it was for patent reasons that they did it. This shows you the full-size Jeff A vessel. You can't really see the skirt at all in this diagram, in this picture, because this, what you think is the skirt is not. This is just an apron that goes over the skirt to reduce the spray. Another curious aspect of the Jeff A is that the propulsion ducts are quite small in dimension compared to the overall dimensions of the craft. I would have thought this would result in a rather low efficiency of the propulsion system. Newton's law tells us that if you're traveling at relatively low speeds compared to aircraft, as air-cushioned vehicles do, you really do want to have large diameter propulsion ducts. So I would have thought that this was not an efficient propulsion arrangement. Here's another picture for historical reasons. This was an artist's impression of the 3K SES. And this goes back again, something like 30 or 40 years. 3K stands for 3,000. The Americans had a plan to build a 2,000-ton seagoing surface effect ship or sidewall hovercraft. They then increased the displacement to 3,000 tons, and hence the name 3K SES. One of the ideas for the bow skirt was to involve not flexible material, but rather flexible, a flexible structure made of some composite, something like a plastic with individual components, which you can see here. So at the time, the joke was that they weren't using fingers, they were using feathers. That was the name of these individual components. I don't know exactly how they were joined together. There must have been some joining arrangement, but I would have thought this would be a very difficult system to maintain. But it was an alternative idea to fingers, the hope being that it might require less maintenance than standard fingers. Here's a picture of the skirt on the SRN2 when they extended it from the original 2 feet to 4 feet. There are a lot of interesting features with this skirt. We're obviously looking at the stern of the vessel. This is the tail end of the keel, which runs the whole length of the craft. You can see it's basically got a circular cross-section to it, semicircular cross-section. You can see drainage holes here because presumably water got into it and they needed to be able to get the water out. The side skirt is quite complicated where it meets the central keel. And I can't actually tell myself precisely what's going on here. It looks like, if you look at where I'm pointing, it looks like these are the two sides of the peripheral jet, which they were still keen on maintaining. And it appears there's a drainage hole here. And one can also see these chains holding the whole wretched thing together. But there would have been a lot of damage to this when running over waves. And I would have thought there'd be a lot of maintenance problems with a skirt like that. It is interesting to see the considerable daylight clearance underneath the skirt. This is the Voyager, which was designed by Bell Aerosystems in the US. By that time, the company changed its name to Textron. And I'm showing this picture to illustrate the complications at the corners at the stern of the vessel. You can see the not only the side skirt here with the fingers below, one can see what was originally a structure called a chip bag, but it's now changed its shape because it's got fingers below it. There's another bag on the other side, and I presume there's a longitudinal keel, which you can possibly see just there where I'm pointing. This is a picture I took myself of an early SRN5 hovercraft in the US. One can clearly see the bags on the two sides, the so-called chip bags, and the tail end of the longitudinal stability keel. This is the VT1 semi-amphibious hovercraft, Thornycroft, and we're looking at the stern of the vessel. One can see here the internal fingers. So to the best of my understanding, there would have been a double finger arrangement. There's the outer fingers which contain the cushion pressure, and then we've got the internal fingers which give you a shape here which hopefully doesn't scoop too much when encountering waves. And this, of course, this vessel couldn't travel over land, and we can see the physical keels that actually go into the water and the water propeller there. And here's a water rudder. This is the AP188. If you look at various pictures of the AP188, there are quite a few different designs of the seals. Here one can see the bag that runs across the full width of the stern, and one can also see the fingers there. I assume that there are internal fingers as well to prevent scooping of those fingers. It'd be interesting to see clearly what's going on here on the corner. The corner is the most difficult part to engineer. Another feature of this skirt is the taper. So it became fairly common with the British design craft to include a certain amount of taper in the skirt. This picture very clearly shows the fact that the skirt is much higher at the bow compared to the stern. This shows you the skirt of the French-designed surface effect ship, the Agnes 200. I'm probably mispronouncing that acronym. You can see the sidewalls here. This is the starboard sidewall. This is the port one. Presumably this red part here is the propulsion system. This looks like the water jet on the port side. What I like about this picture is it illustrates the fact that the stern skirt is basically a two-dimensional structure which is easy to maintain. And then we have the eternal problem of wear and tear, which is very much evident on stern skirts. If you look carefully, you can see these yellow parts here, which suggests strongly that they have some kind of a planing surface at the bottom, which would protect the rubber fabric. This picture again illustrates the taper on the SRN series of hovercraft. Here's another picture showing the taper. This is on the Griffin hovercraft, hoverwork, 12,000 TD. So the height here, the bow is much more than that at the stern. This picture also shows a very large duct. So I would have thought that, or well, I know from Newton's law that having large ducts would provide a much more efficient propulsion system than smaller ones. The reason I'm showing this picture here of the SRN5, this is a very early picture because one doesn't see any fingers in this picture. I'm pretty sure this is one of the very earliest skirts on the SRN5 because it would have been a jetted skirt. The reason I'm showing you this picture is because the next picture is the only picture in my collection showing the bow collapsing in a plow-in phenomenon, which caused a lot of trouble going back many years. So what's happened here is that in some circumstances, usually calm water, and when the vessel is traveling at a high speed, the bow skirt can collapse. This was attributed to some hydrodynamic phenomena, which was cured by putting these strakes on the skirt, One can see them here around the bow. This obviously is an SRN6. In addition to the strakes, which was the purpose of which was to break up the smooth flow of the water, there were also vent holes to lubricate the skirt. Pretty difficult to see the vent holes in this picture. A different way of preventing the skirt from attaching to the water surface and collapsing was to put studs on the water surface, on the skirt surface. One can see these studs here. At this point, the SRN1 had a skirt with fingers which ran about 1/2 of the full depth of the skirt. This is a picture of a Finnish air cushion vehicle, the T2000 class Tuli, which was in the Finnish Navy. This is a model that was tested at the Naval Academy in Annapolis in the US. And I was lucky enough that I was visiting there one day, giving a talk, and it just so happened, with my luck, that we're actually demonstrating a test of a model of this air cushion vehicle in the towing tank. So the skirt arrangement here is different again from what was seen. There are, in fact, pericells, the back to pericells. You can, if you look carefully, you can see the loop shape there. So these are the pericells, like individual cells going all around the perimeter. And I find a couple of features of this skirt fascinating. First of all, they're concerned obviously with longitudinal stability. So there's a transverse skirt there fitted with fingers. And curiously enough, they don't seem to be so much concerned with lateral stability, perhaps because of the pericells providing the lateral stability. An additional feature of this skirt is the stern part of the skirt. That red material, I don't think there's any significance to the color, but there is significance to the material. The inside surface of that trailing skirt is a bit stiffer than the rest of the skirt. And so it's providing a kind of a planing surface there, and perhaps some sort of physical protection against wear and tear. That's more detail of the stern of the skirt. Now, where I'm moving the mouse here, that's the stern, and we're now moving towards the side over here. So you can see these are sometimes called planers, these individual components here. That's the full size T2000 traveling over water. A skirt which I find very fascinating is the one developed in Russia. When I first saw a picture of this vessel, the Mars 3000, I wasn't even sure it was a hovercraft. They've got an arrangement which they called a ballonet skirt. I don't know if I'm pronouncing that correctly. So running along the full length along the side where I'm moving the mouse, that's a tube-like structure, which you can see here. In fact, there are 3 of them, 3 tube-like structures, one on each side and one down the center, obviously to provide lateral stability by subdividing the cushion. I would have thought that this would not be a good design of skirt, because if you get any wear at the bottom of a tube-like inflated structure here, then the whole thing is going to start tearing apart. The big advantage of a finger skirt, as all the viewers here would agree, is that if you wear a bit of the fingertip, the skirt is still fundamentally quite intact. It's quite usable. Whereas if you lose a little bit of the lower part of the ballonet skirt here, I would have thought the whole thing would start disintegrating rather quickly. But one has to admit the Russians have built hundreds, if not thousands, of these vessels. So there must be something in this design. They've got these intermediate skirts here. So this would provide some longitudinal stability. So this assumes that the cushion pressure is higher behind than ahead of these middle skirts. They've also got additional bow skirts here, and then a surrounding skirt there, so which I believe is not a total necessity, but it seems to be fitted to all of these Russian type craft. The trailing skirt again is problematic. You can see how it's been shaped to provide a kind of a planing surface, a flexible planing surface at the stern. As I said, there are hundreds of these vessels built by different companies in the USSR, or Russia as we now call it. So presumably this must be a successful skirt design. A few more pictures of skirt details. This shows you an attachment of the finger to the upper part of the skirt. This is a picture of a worn SRN4 finger. And this wear is not from running over a hard surface like the hoverport concrete surface. It's simply from flagellation when traveling over water. Oh. These are repaired fingers from the MP-PP10, the Japanese hovercraft. If you look carefully, you can see the joints. I'm aware of the time and I will be finishing shortly. I myself have done some research on skirts. I was involved with a number of projects supported by the Office of Naval Research in the US. We did some experiments in what is called the Large Cavitational Channel, which is the biggest such facility in the United States and no doubt in the world. If we just spend a moment looking at the side view here, this is the bow finger. So we built a rig with 5 bow fingers in it. It was a 2-dimensional rig. If you look at the plan view, you can see the 5 fingers. This is a side view, so we see the finger's got an angle of about 45 degrees. And this was very, very heavily instrumented. The letter P here stands for a pressure gauge. So there were many pressure gauges all over the bottom of the wet deck of the structure. And then there were pressure gauges even on the surface of the fingers. There were also cameras. You can see I'm pointing at the camera here. And there are lots of other instrumentations. We had a lot of trouble with the instrumentation. We kind of overdid it. The air caution is in the middle. And this is the planing surface here for the stern. We are, of course, only interested in the bow fingers. This shows you the undisturbed water surface here. This is a rake, which was used to measure the velocity of the water. This channel had a cross-section of approximately 3 meters by 3 meters. So it was a very big facility. This shows you a picture of the inside of one of the fingers in this facility. This particular finger was made of a nitrile material. And the finger has, so in the experiment, we could run the facility at different water speeds, and we could also move the fingers up and down for different degrees of finger deflection. The finger is deflected somewhere where I'm moving the mouse now. The interesting thing is the waves which would develop in the finger. In this particular case, one can see 1, 2, 3, 4, 5 waves, perhaps even more waves. There seems to be small waves there. So the fingers would develop a wave shape, and you can see some instrumentation here on the inside of this bow finger. This shows you a finger with a much greater deflection. So there, you can see how it's buckled in an asymmetric fashion. It's this buckling which causes the wear and tear on the finger. They use this term time of flight camera to take pictures of the seal. The time of flight camera would produce images like that of the shape of the deflected finger. These are pictures, the next two are pictures of some English experiments on the Hovercraft Development Limited HD1 research craft. It's very clear to see how the side fingers are deflecting. That's one picture, and they're deflecting even more. So these are very illustrative of how the fingers work. I'm just going to spend 10 seconds talking about some theoretical work I did. I won't show any formulas because we're running out of time, but I did develop a model. This goes back quite a few years. I did develop a model of what a finger skirt might do when deflected. The blue part here at the top represents the wet deck, the bottom part of the solid part of the hovercraft. This purple line is the side view of the finger at the bow. And in the undeformed shape, it would go all the way down, as I'm illustrating now with the mouse. Now, this is the water surface here. And the idea is that the finger will deflect. Now, one of the difficulties in this analysis is to work out how the finger would deflect in shape. So there are some simple possibilities. The finger could deflect as a simple flat shape, which you can see here, or perhaps it's got a parabolic shape, or perhaps it's a cubic shape. This is one of the unknowns in the analysis. So the finger's got to deflect in some fashion, and this is the water surface. If you do the hydrodynamic analysis, you can show that the water surface actually has to rise a little bit before meeting the finger, and then, of course, it leaves the finger at the trailing edge there. The pressure on the inside of the finger would be the cushion pressure, which I'll call the seal pressure. And then you've got the unknown pressure underneath the finger. There are some technical papers I've written on this subject, which I will not go into now. In the theory, one has to apply a pressure distribution, which I've shown there. And you have to calculate that. That's all in the computer program. We did a separate set of experiments in the towing tank at the University of Michigan to test the theory. This shows you a membrane seal that was tested. And this shows you a system with 5 fingers, which was also tested in the towing tank at the University of Michigan. And I've got 2 or 3 more slides, which I'll show you, and then we can go to question time. I don't really have any time to go into this in great detail, but in very general terms, on the vertical scale is the length of the wetted surface of the finger as it's pushed more and more into the water surface. And on the right-hand side is the cushion pressure. And then we've got to do experiments at different speeds. So these different speeds, in this particular case, this is the speed of 1.629. This is a dimensionless speed. It's the Froude number based on the depression of the finger. And this shows some rough agreement between the experiments and a parabolic assumption for the shape of the deflected finger. This is a picture which I'm quite proud of myself. This is a side view of the finger. So Z here is the vertical dimension, X is the horizontal dimension. This is the purple line, the purple dashed line is the original shape of the finger, and the blue line is the deflected shape. This part of the blue line is the water shape, the surface free water shape. That's all theoretical. The symbols are the experiments. So we had sensors actually mounted on the finger. The experiments were very difficult to carry out, I might say, and I'm very pleased with my friend who actually did the experiments. He went to a lot of trouble to do them. The original points in the experiment are the circles, but because of the difficulties with the experiments, we realized we needed to apply a correction, which I don't have time to apply here, to explain here. The corrections are the squares, and when we applied the correction, we got what I think is rather good agreement with the shape of the deflected finger. This shows you the lift force developed. This LS is the lift force developed on the seal, which also provides a restoring force on the stability of the hovercraft. And this is plotted as a function of the deflection of the finger. So there's some kind of a fair agreement with the experiments, the symbols, and the theory. I've also done some work on the stern seal, and I'm running out of time, so I won't go into that. One can see the loops, which are often used in stern seals, and this shows how the loop is deflected by the presence of the water surface. finally, I have done some calculations applying these theories to actual models. This is a model of a surface effect ship, a sidewall hovercraft. This is all part of a big project supported by the Office of Naval Research in the US called the T-Craft project. The symbol T stands for, the letter T stands for transformable, because the craft was supposed to be able to operate as a catamaran at sea, convert to a surface effect ship in order to travel faster, and then eventually to convert to a fully skirted air cushion vehicle for landing on the water, on the ground. This is a model which was tested by Umo Mandel. One can see the bow skirt with 12 fingers, and they were able to provide me with some experimental data. And just very briefly, just to finish off my presentation, an analysis of a surface effect ship involves a number of components. We've got the wave resistance, there's the hydrostatic resistance from the cut-off transom sterns of the side hulls, there's viscous resistance because of friction on the side hulls, there's aerodynamic resistance because of the air forces on the structure, there's the seal drag, and then the last two, there's the momentum drag, which I talked about before, which is very small, and any air escaping underneath the seal would provide a jet force. So there are a number of components which I've considered. Now I am running out of time, but I'll just quickly show you what I think will be the last two slides. This is a calculation of the resistance of the vessel. It's the model, and this is the model that was built by JJMA, a company in the United States. The length of the model was 4.58 meters, and that's its displacement in kilograms. The experiments are the symbols, and the solid line is the theory that I developed. And this is the theory without taking into account the seal. So the vertical scale is the resistance. The horizontal scale is the Froude number, or the speed. And if we go to this slide here, it's a similar slide. The vertical scale is resistance made dimensionless against the weight of the model. The horizontal scale is the Froude number, or the speed if you wish. That red dashed line is the original calculation of the resistance, ignoring the seals. And my best theory is the solid line. And you can see how it's increased the drag here at the lower speed, particularly at the hump speed. So it would seem that the models I've developed for the seal drag give a pretty good improvement in the accuracy of the theory. You can get a much better idea of the drag at the lower speeds. As a matter of interest, if you look at the actual numbers here, the resistance, this is the total resistance divided by the weight, it reaches a figure typically about 60, but this is 60 by 10 to the minus 3. So in other terms, that's 1/16. That's to say the drag of the vessel is about 1/16 that of the weight of the vessel, which is a very low figure for a marine vehicle. And it shows why an air cushion vehicle or a surface effect ship suffers less drag than a traditional displacement boat. These experiments are done at model scale. At full scale, the drag is even less still. Because of the Reynolds number effect, the frictional drag is much less at full scale compared to the model. So that's the conclusion of my talk. I'm happy to answer any questions. I don't think I've gone too far over time. And thank you, everybody, for joining in and listening to me.
Fascinating.
Well, thank you very much, Larry. That was an incredibly interesting talk. Yes, difficult to know where to start, but yeah, the experiments which you described towards the end are quite an eye-opener, I believe. But let's open it to a little bit of discussion, if we may, and we can stay on as long as you would wish. I should just leave the recording on. Near or Malcolm, do you have any thoughts to offer at the moment?
Okay, Larry, thank you very much for a very nice presentation. You asked me a question in the beginning there about the very deep bow skirts of the SES built by Umo Mandal 10 years ago or something. Because on that vessel we used only finger skirts and no balloon or something, no loop in it. I think it's because of simplicity that you don't have to provide extra air to the loop. So it's everything is supplied by the general air cushion fan. And also this vessel is very special because it's intended to be operated as a crew transfer vessel for offshore wind, transferring technicians from the boat to wind turbines, and that should be done in a high waves. So it's have this extremely high bow height to able to stay at the wind turbine in high waves.
Okay, yes. So it's to do with the operation of the vessel.
Yeah. Normally this would have been maybe 30% lower or something.
Yes, my understanding of the going back many years now, 40 or 50 years, my understanding of the bow and finger skirt is that the bag and finger skirt, my understanding was that the bow was less supple. The bag was less supple than the fingers. So for small waves, the fingers would handle most of the deflection. But for larger waves, when you needed to increase the restoring force, you wanted to have the bag come into play at that point. So I would have thought the restoring force characteristics would be quite different for a finger skirt, which was full depth.
Yeah, but I think that
I guess you've done the experiments and found it was
yeah. But I think the kind of restoring force over the 45-degree forward angle increases as a contributor to the kind of pitch restoring.
Okay, thank you.
Yeah, hi Larry, it's Malcolm Cox here. I hope you can hear me.
Yes, I can.
Hi, nice to see you again.
Yeah.
Thank you for that talk. That was very interesting. You must have a very extensive collection of skirt photographs. There's a few there that I've not seen before.
I have. It's one of my hobbies. My wife is sitting right next to me, listening to me, making sure I don't make too many mistakes. She knows that one of my hobbies is to collect pictures of high-speed craft, mainly hovercraft, but also catamarans. And I do have a very large number of pictures. I've tried to be very careful to attribute the origin of the pictures where I have not taken them myself. But there are many pictures in the literature, and I'm sure there'd be a lot of pictures at the Hovercraft Museum in Southampton, not Southampton, down in the southern part of the UK. I have visited there 2 or 3 times, and I'd love to spend a couple of weeks going through their collection of pictures of early hovercraft. I'm sure there's a wealth of material there that one should all be able to look at. I understand I have heard they intend to scan much of the material and make it available, but that's going to be an enormous job to do that.
Yeah. So a couple of questions I have for you. You mentioned on your towing tank experiments in passing that the material was a nitrile rubber.
Oh, no, we had 2. Sorry, I must interrupt. We had tried 2 different materials. I didn't have time to mention. One was nitrile, and for the moment I've forgotten what the other material was.
Okay. Possibly neoprene, maybe?
I could look it up.
Yeah, but my question was, were those reinforced fabrics? Did they have a base cloth, or were they just pure film?
That's a very good question. I'm pretty sure they were, from memory, they were reinforced. It wasn't just the pure material. It must have been on a cloth backing. I'm pretty sure it was on a cloth backing. Is that right? Is that the answer to your question?
Yes, most likely. But in my experience, once you get down to model scales, it's difficult to find a flexible reinforced fabric of a scale thickness. You either lose the scale similarity on the thickness or you lose it in the stiffness.
Yes, you're 100% right. I'm pretty sure we had endless discussions on that point. It's quite a while ago now. It must be about 15 years ago we did these experiments. You're 100% right. The theory seemed to show that most of the drag comes from the pressure distribution on the fingers rather than the bending of the fingers. So I don't think it would have made a lot of difference, but you're 100% right. I think it's impossible, isn't it, to make a properly scaled finger skirt?
Yeah, so
Yes.
the picture
sure
you had,
right.
the T2000 Thule craft, I mean, that skirt design was a Banlavis design, wasn't it?
Yes, yes.
And they used, well, as I've done in the past, very thin, it's more of a cloth with a skim coat of proofing on it, more like a tent material.
Yes, yes.
And so you end up with something that's believably flexible, but is much thinner than the scale fabric would be.
Yes, yes. You're 100% right. I think possibly anything worse than trying to scale a hovercraft skirt would be to scale the ice in a towing tank test where you want to run the model ship through model. I think that's also very difficult. You can't get that right either.
No, that's right. Yeah, yeah. Well, that's interesting. My final question was on those final drag results you were showing and fitting your predictions to it. You had a peak there at what looked like secondary hump. Is that true? And then the primary hump was not as defined.
I think I've got the slide there. Can you all see the slide there? It doesn't occupy the full.
Sorry, I stopped the sharing, so you'll have to share again.
Oh, okay. No, why is that not showing? Oh, share. Okay.
No, yeah, okay.
Yeah, okay. It's not full screen, but you can see the. I'm pretty sure this is the standard hump that one gets at that Froude number. See, the Froude number is a bit less than 0.4, so I'm pretty sure that's the standard hydrodynamic hump that you get at that. I suppose I should pull out my slide rule after this presentation and check that. But of course, the drag increases at higher speeds beyond the hump drag because of the friction on the side hulls.
Yeah.
Yes. Okay. Yes, but I did try different shapes here. Sorry, first of all, I tried just the friction of the seals. So this red line, the red line here is ignoring the seal altogether. The orange line is the friction on the bow seal. The green line is friction on the bow seal plus friction on the stern seal. And then the last three curves showed different kinds of more realistic models of the fingers, where I also look at the proper deflection and looking at the pressure distribution. So I looked at flat friction plus a flat shape, friction plus a parabolic shape, and friction plus a cubic shape. But it seems to me like the last theory is reasonably representative of what's really going on. So it does seem to give a reasonable indication of what the drag is. There are a lot of difficulties with doing an experiment like this. And one of them is to know what friction factor to use. So I've got a friction factor of 1.18, which means I've assumed the normal friction line. I've used here the ITTC friction line for a flat surface, but I've increased it by 18%, and that gives me the friction on the side hulls. But the theory does include the wave making of the side hulls and the wave making of the air cushion as well. So it's a pretty complete theory.
I know in some of your previous work, you've looked at wave-making cushion perimeters and whether they're hard-edged in terms of.
Yes, that's right. Oh, that goes back. Yes, that goes back longer than I care to imagine. That goes back almost 60 years now. Yes.
Yeah. Or whether the transition from the cushion pressure to the external pressure on the water is a gradual one.
Yes.
How do you think this theory with your parabolic theory ties into that? Because on an amphibious craft, you've obviously got this effect all the way around, haven't you?
Yes. Okay. So in this theory, that's a very good question. I have to think for about 2 seconds. In this theory, the pressure drops off instantly on the sides because you've got the side hulls, but at the ends, I've used some tapering off of the cushion pressure as you've suggested. So the pressure does not drop to zero suddenly at the two ends, namely the bow and the stern. I have used the smoothing parameter, and the smoothing parameter I seem to use has got a value of 10 in dimensionless terms. So I could send that information to you if you're interested. But I have used that smoothing parameter. Yes, I've still got that in there after all these years. Yes.
Right. Okay. Yeah. Well, thank you. That's a very interesting explanation.
Larry, I have can I have an extra question?
Yes.
Yeah, I've recently, the last 3 or 4 years, done 3 series of model testing of SES. And what we found is that running trim of the vessel is really important for the resistance. And what we have experienced is that we're using your theory for prediction of the resistance, and this is at high fluid numbers. Then if we are far off, we know that the trim is wrong, and we can optimize the trim, and then we can come down to your resistance curves. So that's a very good tool when doing model testing, because trim is seems to be a very important factor in the total resistance of the vessel. And you as a kind of operator of surface ship, you should be very you should have good control on the running trim of the vessel.
I'd be curious to know, Neil, how the operator does control the trim, and how does he know that it's the best trim when he's operating the craft?
Yeah, that's good, because you find the best trim during model testing.
Oh, doing model testing.
Yeah, and then we just measure the trim on board with a trim meter, and we ask the captain to run at this and this trim.
Oh, I see. You don't do it. I see. You've pre-calculated what.
And we use interceptors in the stern, which is really effective in providing the kind of lift force in the stern to provide the correct running trim at high fluid numbers.
Okay, I haven't done the calculations myself, but I'm thinking on the fly at the moment that the optimum trim that you're talking about is obtained by minimizing the interference of the skirts.
Exactly. So if you have a camera inside the air cushion pointing forward or stern, you can see air gap below the
see now you've got
stern and bow skirts if you've done it correctly.
Ah, yes. Oh, that's interesting. Yes. Thank you for that information, Nia.
Yes, as a comment, Mike Moon speaking.
Oh, you're very. Can you speak louder, please?
Can you hear me at all?
Yes, now I can. Yeah.
Is that any better? Yeah, right.
It's a little bit.
You were talking about puff port and skirt lip, where you had hydraulic rams operating the skirt lip, and later puff ports were introduced. When we were operating Mark 5 SRM5s and SRM6s, we had both. The hydraulic rams lifting the skirt, one at each corner. So if we pulled the control to the right, it would drop the skirt on the left, and the craft would lean to the left for attitude. With the plough, I was doing 60 knots down the Norwegian fjord and introduced a plough with
Yes.
rudders, with all the elevators off, all the ballast off. It was still nibbling. The only thing that saved it was the skirt change, pulling right back on the lever and dropping the rear bags into the water, and it brought the power up.
Oh, yes. Okay. Was that a deliberate experiment or an accident?
I was carrying 60 Canadian troops down this fjord, and we were being chased on an exercise by our aircraft. And that's when she nibbled, because the fjord was dead smooth.
Yes.
And she just started nibbling it quite the bloody life out of me.
Oh, so that was an interesting experience for you then.
There was lots of them because we were an experimental unit. Providing we didn't exceed 30 knots, we could do plough turns. And an SN 6 Mark 2 and an SN 6 Mark 5.
Okay, interesting. Yes.
And also we could pirouette the things as well down the Solent and other places.
Okay.
It was fair game really, because we had sort of free license to do whatever. All right, we had to do certain operations and fulfill certain tasks, but we were free to experiment to see what the actual capabilities of the craft really were. So we used that to its limit.
Okay.
Hell of a good game. Yeah, it was.
Interesting that, that this happened when it was glass smooth water as well, rather than in waves.
Yes, I found that interesting when I first read about
going
it.
down that fjord, you could actually see in the water the reflection of all the mountains, everything in the background, which is in colour.
Yes, I believe
underwater and over water. Absolutely.
I might have read about that incident in Norway. I might have read about that many years ago.
Yeah, Larry.
Oh,
sorry. After Mike. Mike, you have a question.
I just want to make an observation that obviously my experiences with light hovercraft, which were operated over all sorts of different surfaces, and most of your work has been done over water.
Yes.
Now, I had the opportunity now and again to compare my craft with a BHC craft, which the bag and finger skirt, on different surfaces. And for example, in New Zealand, I found that I could easily operate over very soft mud, whereas the SRN6 couldn't do it. And another occasion, I remember the BH7 having great difficulty going over shingle on Brighton Beach. And of course, with our small craft, the biggest obstacle was long grass. We could operate quite happily over short grass, but thick vegetation was always a problem.
That's because the lower edge of the skirt was kept away from the solid ground underneath, and you're getting leakage underneath the skirt. That was the problem, wasn't it?
I think it was, and just the drag of the grass.
Well,
but what I'm trying to point out is that you can learn an awful lot from the seat of the pants rather than the laboratory.
of course, yes.
Yeah, if I could come in here, I'd like to kind of ask a question as well. Going back to your experimental results, Larry, I'm interested to see that the curve which fitted best in terms of the drag results was the parabola rather than anything else, and I'm likening it to the surface shape which comes from the transom of a planing craft, and I'm interested to your thoughts on whether there is a link in the response of the surface in that way.
Well, it would be nice to do a more complete theory where you look at the structural interaction between the skirt and the water, and I haven't actually done that.
No.
That would be the thing to do. It's
Yeah.
actually a very the idea of calculating how a finger crumples or collapses,
Yeah,
as it interacts with the water surface. I think the physics of that problem are unbelievably complicated. I do have a friend in the US, whose name I've just escaped me at the moment, who did a PhD on the subject, but I thought he was awfully brave doing research on trying to work out the actual way the finger collapses on encountering the water surface. He got his PhD, but he ended up working on a very, very simplified version of the problem. So I think some of these hovercraft problems, particularly the skirts, almost defy full proper analysis. They're so complicated. And as it was just suggested, perhaps even just a full-scale experiment is the simplest way to find out what's the best design. Yes.
Yeah.
One thing that just crossed my mind while preparing this presentation of what was the true origin of the finger skirt. And if my memory serves me correctly, I seem to remember some pictures of a Land Rover, which is normally a four-wheeled craft, which could get bogged down in very muddy ground. And I seem to remember that they fitted a Land Rover with a skirt, and I'm talking about like 1962 or 63, something like that. And the skirt was what they called at the time a convoluted skirt. And I think it was a full depth finger, went from the chassis, the bottom of the car, right down to the ground. And they called it a convoluted skirt. I was quite young at the time. I don't think I knew what the word convoluted meant at the time. But I think that convoluted skirt was the origin of the idea of a finger, which seems to have become now universal.
I think Malcolm might have the records back from HDL as to who actually claims the origination of the.
Yeah, that vehicle was called the Vickers Land Rover.
Oh, right.
Yes.
And its skirt was not fully self-supporting, so it required. They were tubular fingers, and they didn't have an external face angle. They were vertical.
Yes, yes.
It required a super pressure inside to make these tubular fingers stand up. I think the breakthrough came from Dennis Bliss, who worked for Hovercraft Development Limited, who came up with the classic finger made of a triangle of material that didn't require any super pressure. It was self-stable.
Yes.
The crucial feature being a 90-degree bottom angle,
Yes.
which when you unfolded the triangle of material was actually a straight line.
Yeah.
Yes, yes.
Now, people like BHC and other skirt designers, they played around with that slightly and took a few liberties with that straight line. And they cut the tips off and did various other things. But basically, the fundamental principle of the finger is that it's self-stable just with a simple pressure behind it. And because of those various notable features, Dennis Bliss, through HDL, was awarded the patent for that device.
Okay.
And
Yes.
HDL had that patent running for about 20 years.
But from my point of view, it seems to be the miracle of the finger is that there are no joints at the bottom to be worn by either the ground or the waves.
Yeah, and they always they reinflate pretty instantaneously, which is quite a nice feature. And of course, if you pull one out, rip one, then the adjacent fingers expand to fill the gap up.
Yes, yes, yes.
It's a fairly damage tolerant seal system.
Can I chip in there?
Please do, Mike.
I use the HDL loop and segment skirt system on all my craft. I had a little problem on the largest craft, which is the Skimmer 12, of lateral stability. And I'd like to thank Malcolm for inventing his skirt shift system, which helped a great deal in trimming the craft and also coping with side winds and off-center loads. And that helped a lot. I think that is still being used by Griffin.
Yeah, it's still being used, but I can't claim to be the original inventor, just one of the development team. So my name doesn't appear on the patent.
Okay, I still think it was your idea, and you certainly helped to develop it.
Yeah, it was quite a long development path to make it reliable, I have to say. But yes, Griffin still used that on their smaller craft. The 8000, 8100, 2000 models all use that skirt shift system. Which I suppose in principle was not dissimilar to the VT1 that Larry showed earlier on, except instead of having a direct pulling system, which was operated by hydraulic cylinders on the VT1, the HDL system used a herringbone shape of cables that enable you to operate it from a single point up forward. So it removed all the mechanical clutter from underneath the craft and kept it out of the way.
Could I ask a question? I'm not sure if best answered by you, Larry, or perhaps Near. I'm intrigued by the sealing of the loop skirts at the stern of an SES. And the stabilizing of that end surface against the hulls. How is that achieved?
Before Near answers, I believe there are two schools of thought on this. One is you don't do anything, you just try to make it a close fit. And the other theory is that you put a panel at the end, so that the trailing
is an inflated bag.
Yeah, so it's more like a bag, but I think both methods have got slight disadvantages. That's what I've heard, but Near, of course, has much more experience. He must know the answer to that question.
I have only experience with open sides. So it's inner side hulls which are closing the stern seal. So it's a small gap over half an inch or something. But that is sufficient to close it, and also there is separate fans blowing, having an extra pressure in the bag fan, in the bag system bag, in the bag itself. So it's a kind of 7-8% overpressure, and that is maintained by a separate fan, and the leak flow through that is, of course, some of it is leaking towards the side hulls, but most of it is through special openings in the lower loops.
Okay, but there's no stiffening at the edge of the
No.
loops.
It's a completely two-dimensional structure. There is nothing kind of in the longitudinal direction at all. It's there's some inner kind of what you call it. Supporting structure, but that is still two-dimensional.
Okay.
Near, do you have a planing surface on the bottom of your bag?
No, there is no planing structure, but the thickness of the stern skirt is a bit higher or thicker than the bow skirts.
Oh, okay.
Yeah.
So it would be a bit stiffer there.
And at optimal high speed, there is an air gap. So there is no friction between them. So it's a few centimeters of air gap.
Oh, okay.
Yeah.
So there's no almost no friction.
Yeah.
Okay. Thank you very much indeed, Neil and Larry. Okay. Is there any other questions, or shall I bring this to a close this evening? My time, morning in Australia, of course.
Yes.
Okay.
So,
well,
so Alan,
thank
I'll
you.
send you the PDF if people would like that.
Yes, please. Let's. I'll at least offer that for distribution. Yes.
Yes. Okay then. Good. Well,
Yes.
thank you again for joining me on the presentation. Then.
Well, yeah, the presentation is recorded. We will put it on the YouTube channel so that the rest of the members can take a look at a later date. I put a small item in the chat, and there's a couple of others which have come up. They get recorded, so I shall be able to answer those and come back to you on that.
Well, if I could
So-
thank Lawry Doctors for a very fine presentation, very well put, and answering all the questions, and to everybody that tuned in to watch the presentation. I'll hand over to Alan for closing the presentation.
Well, thank you, everybody. I will call the meeting a close now, and really appreciate your presence this morning and this evening. I hope to see you again soon.
Thank you,
Bye-bye then.
gentlemen.
Thank you.
Bye-bye.
Goodbye.
Bye.
Bye.
Bye bye.